So if we have this absorbance data and we've converted it to cells per mil, we're ready to graph the data. And I'm going to show you first how to graph this on just regular old graph paper. And I think as we do this, you'll see the problem with regular graph paper using data like this. So we have independent and dependent variable. The independent variable is the one you could write down before you started the experiment. It's not the result of the experiment. So in this case, it's going to be time. Time is our independent variable because we knew before we started that we were going to check the samples every 30 minutes. We always put the independent variable on the x-axis of a graph, the horizontal axis of a graph. So we want our horizontal axis of our graph to have from 0 to 120 minutes. So we can put 0, 30, 60, 90, and 120 along here. And please notice how I space these out equally between them because there should be an equal distance between 0 and 30 as between 30 and 60 as between 60 and 90. There's a linear relationship. All right, so if we look on the y-axis, we're going to plot data from 5 million all the way up to almost 5 billion, almost a billion, so 790 million. So that means that our y-axis is going to have to be pretty stretched out. We want data from down here to be close to, it doesn't have to start at 0, right? It could start at 1 million, for instance. About halfway through it needs to be about 500 million, and all the way up here needs to be about a billion. Or so if this is going to be a billion or 1,000 million, if you will, see, this could be times 10 to the 6th, then halfway down here is going to be half of that, or 500 million. And all the way down here can be our 1 million value. Or 1. So sorry, this is 500 million, not 500,000. And up here is a billion. Okay, so the data we have to graph is from 5 million all the way up to 790 million. And so 5 million is going to be way down here at the bottom. You're barely going to be able to see it on the graph, right? Because if this is 500,000, then halfway between here is 500 million. This is 250 million. And so this is going to be 100 million. So 5 million is going to be a teeny tiny little bit down here, somewhere around there. And same thing, our next one, if this is 100 million, 15 million is also going to be very low down here, somewhere between, this is say 100, this is going to be 50 million, this is 25 million, so 15 million is also going to be way down there. Then our next data point is 63 million, so we can use that kind of guesstimate value. If this is 50 million, and this is 100 million, 63 million is going to be around there. And then our next one is 560 million. So now this one is going to go all the way up here to 500,000, and then just above that, somewhere around there. And you're going to do this a little bit more carefully, count this out. Then our last data point, 790 million, is going to be up here. If this is 500 million and this is a billion, then 750 is about halfway between here, so somewhere around here. And like I said, count it out yourself, don't just guesstimate. But this graph is going to look something like that. And this, when you connect these dots, is going to give you sort of that J-shaped curve we were talking about in the previous lesson. Be sure once you have your graph worked out that you go ahead and add a title as growth of E. coli over time in X media. And make sure you add labels on your y-axis, again, making sure that your y-axis is spaced out accordingly. And this is cells per ml. And down here is time, and our units were minutes. So now we're going to look at how to graph this data on Semilog paper. So in this case, The same situation applies, that time is our independent variable, and that goes on the x-axis, and then cells per mil goes on the y-axis. Now, the benefit of semi-log paper are a couple. First of all, you can get data on the page that are vary quite a bit in their orders of magnitude. So you notice here we go from 5 million all the way up to almost 1 billion cells per mil, from 10 to the 6th to 10 to the 8th. So we have 3 orders of magnitude, 10 to the 6th, 10 to the 7th, and 10 to the 8th. So I'm going to choose 3-cycle semi-log paper, which means that there are 3 sections, one for each order of magnitude, 10 to the 6th, 10 to the 7th, and 10 to the 8th. So I'm going to show you how to label up these sides. So you choose a number of cycles you need based on how many orders of magnitude you have. And then this section refers to the 10 to the 6th value, the lowest one. So the bottom here is going to be 1 million, or 1 times 10 to the 6th. The top value is going to be 10 million. And then this is going to be 10 to the 7th. It's going to be from 10 million to 100 million. And then 10 to the 7th, this one is going to be 10 to the 8th, which is going to be 100 million to 1 billion. So as we go here, we're going in orders of magnitude. If this is 10 million, this is 20 million, this is 30 million, this is 40 million, and so on like that. So 500 million would be here as opposed to halfway between these values. Again, on the x-axis, we're just going to have time. So we have 0, 30, 60, 90, and 120. Again, this is time in minutes. And then let's take a look at the data that we want to graph here. We have 5 times 10 to the 6th, 1.5 times 10 to the 7th, 6.3 times 10 to the 7th, 5.6 times 10 to the 8th, and 7.9 times 10 to the 8th. So we're going to start at the 10 to the 6th, and 5 times 10 to the 6th is, here's the 5, so this is going to be 5 times 10 to the 6th right there. The next value is 1.5 times 10 to the 7th. This is 1 times 10 to the 7th. This is 2 times 10 to the 7th, so halfway in between there is 1.5. So that would be there. Then we have 6.3 times 10 to the 7th. So 6 times 10 to the 7th is going to be all the way up here. Remember, we're doing 60 minutes, so we'll go up. And 0.3 is going to be about there. Next one is 5.6 times 10 to the 8th. So we're at 90 minutes. The 10 to the 8th region, 5 is there. So 5.6 is going to be, sorry about that, I'm off the page, all the way up there. And then the last one is 7.9 times 10 to the 8th. So here that'd be about right there. So we come across and label it right around there. So graphing on semi-log paper, we're going to look for the region where the data appears to be forming a straight line. And that's going to be the region where we see exponential growth. So you kind of have to eyeball this and get a sense of where you think it looks like the data is most likely in exponential growth. I'm going to say somewhere around there is probably the region at the beginning of this where the cells are growing exponentially. And then if they were continuing to grow exponentially, you'd see something like that. So maybe this one and maybe this one is just an outlier there. So that's how you would graph that data on semi-log paper. And the benefit of this is that we can see the region where the data forms a straight line. That's going to be the region where the cells are undergoing exponential growth. You wouldn't necessarily connect this straight line all the way because you may have found that, in fact, this data point was here or something like that, and so that this would actually just be leveling off at that point. So it's not a best fit line, but you do want to find a region, see if it looks like there's a region where your data is forming a straight line, which gives you an indication that there's probably exponential growth happening. And again, don't forget to label this. So we want cells per mil on this side, and up here you would want to put a title of some sort.